Okay. Okay, here we are. So I think we can start with the discussion. Lydia, I don't know if you have a general comment while I try to find some questions from the participants.
Well, my general comment would be if I was a potential user of the tools and listening to this presentation from the point of view which tool to use, that I would be completely confused. There are so many tools doing somewhat different, somewhat similar things. So which one is the right one for me? I'm not sure whether the tool developers are able quickly kind of to play devil's advocate and say, well, this is not good for this or this is good for this, to start the discussion.
If I may I?
Yeah, go on.
Yeah, I would say that the impression I got is that there are different approach in the way that, for instance, the tool we have been developed is more oriented to engineer in HVAC field to manage or to redesign system, looking at air distribution through the HVAC unit and to avoid that you can move from one room to the other room due to recirculation, the virus. Other tools are more epidemiological based, trying to assess an overall risk. Why we are not doing that, as I was stressing, is a tool to try to optimize the system and not be used to say that you have or not really a risk, because the uncertainty is still very high on the input data we have. Other tools are, in my opinion, more oriented to management, just like what you can have with the air quality or with the CO2 concentration or with the temperature and humidity inside. And then you have another parameter, which is the COVID risk, let's say. Then it's to be used by final user somehow. But then the point is that still the uncertainties about the indicator are so high that could be dangerous, in my opinion.
Okay, we have the first question from Paul Hewitt for all the panelists. Paul, can you talk?
Well, I have my microphone on. Do you hear me?
Okay.
Yes. My question, having done some of the modeling myself using the Wells-Riley infectious disease model, it is centered around the emission rate. We had presentations of several tools ranging from very, very slick to less slick or nicely presented. But to me, what I tuned in for was a discussion of the emission rate source for these models. That is a critical component, as we probably all recognize, but we hear nothing about it in the presentations. I'm finding I'm probably going to have to go to the websites and try to dig into it. But to me, only the last presentation mentioned their emission rate source based upon the restaurant scenario. I think that was in Korea. None of the others mentioned this critical component, and that's what I am interested in.
May I answer to this? Actually, my tool, the indoor scenario simulator, is all about the emission source. And actually, my talk starts with how I model with the Monte Carlo simulation, the emission rate. And I think this is one of the key points that we must be aware of. If we are modeling or calibrating our systems, our approaches with super spreading events, we are calibrating it most likely, at least that's what my tool suggests, my modeling suggests, we're calibrating it with the emission strength of people that have very high elevated virus levels in their body. And the problem why, why it's decisive that we understand this is in our communication. It's not every person that is sick will have that rate of emission. And only in my modeling suggests that you have about 10% that start to actually become of the infected people that are a problem for airborne transmission. And only about 1 per mil are those that create super spreading events. And if you then go into a hospital and you tell them that you have to be careful that every of these people is highly infective, you will not meet their reality, that most of the times they can go in with simple hygiene masks into a room and not get infected. And they will attribute just careless hygiene measures that they have 1 in 10 of their staff getting sick when going in to such a room with poor hygiene measures, with like not a well-fitting respiratory protection. So the moment that you explain them that not every of their patient is highly infective by aerosols, but some are, they may start to understand where their reality meets with your model.
If I may complement the answer, the point, in my opinion, is that it's like when you have an anti-fire system. You are not looking at how will be important the fire you can get inside your building. You just design the system. If there will be the fire, the system has to work to catch the fire. That's the point. Then we have all the input available today, published in the scientific literature as input, but with the uncertainty we still have on such input. But the question again is to use in the correct way the tool, just looking how you can minimize the risk. You can avoid, and you cannot say that the risk is exactly a certain value. Forget it.
Yeah, if I can add to that as well, I think the summary that Livio made at the beginning was absolutely spot on. I think what would be most useful after this would be sort of organizing the different tools into a fit for purpose chart. Which ones are aimed at designers, which one are aimed at communication to general public, which ones are aimed for operations. Because I was definitely seeing a range of different fit for use there, different user types, but also the once we have designed this, so once we have gone through these tools, and if I'm an engineer and have figured out how I want to optimize my system, how do I check if it's actually working and tracking the results from there? And so if I go back to the emission rate source, this is where if we take the design data and then go and verify if the results are actually working and start closing the loop on the research, then the type of data we need at the opposite end of the spectrum is completely different. Things like emission rate source don't matter if we're measuring the airborne particulates from 0.3 to 10, for example. They matter heavily in the design stage, but once we're in the operational and we're tracking the data, what matters is the actual results. So taking the tools and breaking them down into fit for purpose, I think would be a very helpful next step to steer people towards where they are in their process and what suits their purpose best.
I think it's useful also when you look at the tools across the different tools and you kind of do a sensitivity analysis. Clearly, the emissions have a very profound impact on the model's outcomes. And other factors such as breathing rate also have a significant impact. The ventilation rate has a big impact. But then there are other factors and the use of any type of masks. But if you almost rank order these, some of them, such as the use of a relatively small air cleaner, doesn't have that much of an impact on the air, on the risk of infection. But clearly, any assumptions that we use in terms of emission are going to be, profoundly impacting the results of the models.
Okay, we have also some, I think a couple of questions from William Mills. Are you there, William?
Yes, hi.
Okay.
I guess my camera's not working, I don't know. One of my first questions, I think, was about the use of the Wells-Riley model, in that I think there's a number of occasions where it actually doesn't work that well and seriously underestimates the aerosol transmission and aerosol transport. And so was a little bit surprised to see that still being used, unless I missed something in the 5-minute presentation. I was wondering if the people who talked about using the Wells-Riley model, have they adjusted it for the much more recent data showing how it seriously underestimates?
Well, I'll make a few comments. Clearly, all of the models are very approximate. And not only is there an issue with the Wells-Riley, but just using the compartment model, we're making the assumption that there's uniform concentration in the space. And as the space grows larger and larger, that assumption becomes less and less valid. If you have a person standing in a large hall, obviously the gradient in emission from that person is not going to be uniformly distributed between many square meters. So each of the models are working from that as a limitation. The question is, as you get more and more complex, for example, if you begin using computational fluid dynamics or other types of ways to get a better estimate, it just becomes so much more complicated that the utility decreases. So, you know, as long as everyone is keeping in mind that these are order of magnitude estimates and not intended to be exact estimates, I think that they can be useful in you know, a societal context, but perhaps not as accurate as we would like them to be.
We're doing some work with some open source computational fluid dynamics that I think are going to hopefully address some of, you know, not having to have, you don't have to have ANSYS and that sort of thing. So it'll be interesting to see how work from that compares with this type of model. I think Paul Hewitt did a nice set of articles there in 2017 on indoor air models, the 4-part series on the near field, far field, that would be useful for everybody to take a look at. And then the other question I had, and I guess it goes the same thing, was really just, I was surprised at where the SCOH model indicated only a marginal impact of ventilation. Maybe it had to do with the ranges, but work we've done, I mean, when you start getting in 6 air changes in the US, we'll say 600 square foot classroom, you're starting to get in the range of 90–95% efficiency if you're getting removal and full mixing there. I would say that is a pretty significant impact on there. So I was a little bit surprised to see them saying that in their model they weren't seeing that much an impact from our ventilation, but it might have been at lower air exchange rates and not including like filtered air or something.
Maybe I can answer directly to this. The statement was not that ventilation has no influence, but if you are in a clearly unsatisfactory situation, it's difficult to overcome the situation with ventilation alone. So in many cases, putting on a mask will be sufficient by itself, whereas in the same situations, increasing ventilation is in many cases not sufficient as a standalone measure. So I didn't want to say ventilation does not work. It does work as a supporting measure, and it is important that we ventilate well.
My model addresses the same issue by treating the mask wearing, ventilation per capita, and proximity as 3 separate values, all affecting multiplicatively into the same direction. And the impact of that, which I found interesting, and was the sort of the first reason why I started playing around with this Excel tool was that I found that when you put these things together, these three factors together, the sum effect can be immense. It can easily become 1,000-fold or 10,000-fold even in the otherwise similar setting. When you add people to the room, you not only reduce the ventilation rate per capita, but you also reduce the distances between the people at the same time. And those add on top of each other. And that can bring rather surprisingly big effects.
One comment which I have, if I may, I like very much the idea of putting some classification about the tools for the user to be able to make a decision what's appropriate for what. But also, many colleagues ask us question or ask, can you use my tool and check how it works, a sanity check. I think, Matti, you used this term. The problem is that no one really has time for playing with others' tools. It's very difficult. But if we could come up with a standard scenario to which for which we would apply all the tools. This is by comparison with instruments. Ever so often there are big campaigns comparing instruments. So all the instrument developers bring the instruments and there's an experimental chamber filled up with specific pollutants and so on. If we came up with this kind of a scenario and we applied the tools to this scenario and then compare the outcomes, that would be one way of, well, first of all, the sanity check for all of us, how they work, but also would help us answer how they are best applied for different applications. Would this make sense?
Yeah, that is a great idea.
I think it makes very much sense, and I could actually offer something. I'm not just modeling theoretically, but I'm actually, because of the reality is different than often than the theory or like what you calculate. When I do consultancies when I study this on-site, this question, I use the tool to understand whether I'm probably in a good or in a bad situation. And then I go in with test error results. I release the test error results, and I have an array of sensors that I place all over the room to understand what is the actual concentration development. How does the real air exchange, like real in the sense of how quickly does really the aerosol decay. I'm using a test aerosol of about 1.4 micrometer, which is pretty much in the range of what you expect from being exhaled by people. And if I go to these places, I could actually offer that people, that I share the situation of the room with the people, and they can send me, the different developers can send me their findings, what they would see for such a room, and then we can compare what we find in the aerosol decay in this room and what it means later.
Okay, we have now a specific question from Robin Schofield. Robin, are you there?
Yes, hi.
Okay.
Yeah, just a question. I think it's been answered actually, but I was the reset program, which I think is one of the few which takes into account the environmental parameters such as relative humidity and temperature into the risk, and I found that really interesting. It's something that I certainly want to spend a lot more time on. We have our own sensors, and so I was wondering if we could somehow how much the science is open, really. I understand you're a consulting firm and have your own sensors, so I just wanted to find out how open you were to collaboration.
Yeah, thanks for the question. I'm happy to answer that one offline too. We actually write standards, so we don't really do consulting, and we don't make or sell sensors either. We collaborate with sensor providers where we test and accredit the accuracy, and we make the math available to them. So there's a number of sensors that plug in, send us data, we compute the results and send it back. So from that perspective, I'd very much welcome Lydia's suggestion on an open model to input all this data from a whole bunch of different sensors, compare all these different sensors, the results plus the before and after of here's the design estimation, here's the measured, with a whole range of different monitors. And so in a case like that, that would be fully second that opinion. But getting back to your question, for us specifically, and happy to answer more offline, but we work with a whole range of different monitoring companies, and we'll be making the different algorithms available for people to build directly into their sensors. A lot of the question there also goes off of William's comments, where because we're assessing in real time, the Wells-Riley formula didn't work for us at all. And so had to look at a completely different set of formulas to look at how to evaluate real-time data, but it will be made available.
Okay, let's go to a more general question from Raya Singh. Raya, are you there?
Yes.
Okay.
Thank you very much. My question is same as what has been answered before. It is regarding, like in New Delhi, there is very high pollution levels, ambient air pollution levels. And we have advised a lot of buildings to have ventilation so that the ventilation can help in the COVID scenario. So what can be a good solution in buildings in India, especially in New Delhi, where the pollution levels are high, but we want to ventilate the buildings for the disease transmission prevention? Hello?
Yes.
Use filters. Filter the air before to put inside. This is the only way you can do.
Can we also use UV technology? Is that a good option that anybody has explored here in the webinar?
Well, we are working with UV technology, making experiment on the virus. The point is it could be useful because it's already used for other kind of virus, for other kind of bacteria, and so on. The question is to calibrate exactly the wavelength to be effective, because if you move some micrometer far from the right position, let's say right wavelength doesn't work, 100 or 1,000 is the difference between effect or not effective dose. And then the system should be designed correctly, depend on the flow rate you have, because you need a certain time to radiate the virus. Then we are working, other people are working on, I don't know when will be ready some equipment on the market.
Okay. Thank you.
You're welcome.
Okay, I suggest to use the session query and answer only for questions, because it is not easy for me to understand if there are other questions.
If I can, Giorgio, make a comment. Yes. We should make sure that we copy, before the end of the webinar, we copy all the questions, comments, and so on, and put them on the ESIAC website together with all the material. Yeah. Because they may, others may respond to this, to the questions which we are not able to respond during the session.
Okay, I think that we can start with the second video, and then we will have more time for the final discussion. Okay, let me. Okay, here we are. Are you there?
Yes, we are here.
Okay. we have, okay, after all these tools, we have another question from Alireza. Alireza. Okay, you can talk, Alireza.
Thank you for presentation. I think it's nice. So, different. My question is, when you recommend some calculation, I mean, in the most of the time is question about mixing of the air. But actually, I mean, in open plan offices, we don't have mixing. It's a very large room, and you have a lot of different concentration in different places. How do you handle it in your calculation? That was my question.
Maybe I can answer to this. I see the calculations with the well-mixed room model as a baseline to start off, to tell somebody where is the situation. So if you have a well-mixed room, this is the baseline. And now when I go to recommendations to like theaters, for example, I go to their place, I have a look at it, I use test aerosol to see the behavior of the aerosol, and I measure with an array of sensors what actually happens with the aerosols, with the test aerosol, how quickly does it really get removed from the air. And this way you can say, for example, okay, we have now here this air cleaning device, we use it, we don't use it, and then you check both times the real removal rate, which I can then use again back in the model and say at this workplace, the air removal rate in the sense of how much aerosol gets removed per time unit is this much. And this way you can basically recalibrate the system and then still use this tool calculator to come up with an estimate of how is the situation at the place.
If I could comment as well, I think in most open plan offices, if there's air conditioning and there's a central HVAC system, even in a heating mode, in a variable volume system, you're going to get 2 or more air changes per hour. So I think that you are going to get in a mechanically ventilated room, reasonably good mixing of the air. Perhaps if you're looking at a room that has no mechanical ventilation or a residential environment where you could have very, fractional air changes per hour, then I think the point would be particularly relevant.
I'll add to that as well, if I can. I think Michael's question or Michael's answer sort of addressed both sides of this. I mean, one on the mixing, I definitely recommend get yourself a monitor, rent one, whatever, walk around the space and get a sense of mixing for your own space, because every large open space will be different. But that's the mixing portion. The other portion is the removal. And this is something that we haven't seen factored into any of the calculators right now, the predictive calculators, is in the research, in the monitoring research that we've been doing. There's a very, very big difference between portable filters that are put on the floor and those that are bolted on the ceiling, for example. And when you're putting a filter on the floor, it hits furniture, it hits chairs and tables, and the airflow gets very much compromised. And so complete mixing is one thing, complete removal is another. And I'm just in answering the second part of that one, I think that's a missing piece that we're gonna have to see in the calculators that help identify air cleaning technologies, is where are those located to account for turbulence and interruptions in airflow.
I may just add that my observations in real buildings, I have made 3 types of observations. One is you have, or 4. One is you have really a well-mixing room. The second one is you have displacement ventilation where fresh air is coming in from below, it goes up, is sucked out above, all is fine. A third variation is that you have kind of strange situations happening. One room we saw at about 1.5 to 2 meters altitude, all the aerosols accumulating, making kind of a fog layer exactly in the level where people walk and stand around. So you cannot go around and do real testing on site if this is a place where you have many people go around, and it's very critical that you get it right there.
Well, just to complete, my tool have, for instance, the efficiency for ventilation. That means removal efficiency, that you can play with this number, but it's a number. When you have displacement ventilation, you can have 1.2. If you have mixed ventilation, you can have 1. If you have bad ventilation, you can have 0.8. But the problem is how to give a real meaning to such a number. That's the point. Again, input data.
May I continue with my question again?
Yeah.
Yeah, my question is actually a new question. I look at the air cleaner in a different places, and the effectiveness and the efficiency of air cleaner in offices and so on. But I found it that when you test it in a laboratory, you have, for example, 90% efficiency. When you have it in a real room, so you have it between 26 until 50-55% efficiency. What's the reason that we don't have, I mean, the number that we can get it in a laboratory?
I'm glad to hear that you're testing. I mean, there's such a difference between what's tested in lab and what's happening in reality. There's a number of answers to that question. I'm sure others will have more, but a lot of the filters that are out on the market are electrostatically charged to basically upgrade the rating of the filter. By the time you ship that filter to the market and put it out into the field, the electrostatic charge on the filter is gone or is in the process of disappearing. So that'll dramatically change the test result from the lab, where it's in a perfect condition. The electrostatic charge on the filter is good, and by the time it gets out into the field, where that charge is gone. That's one of the many answers. But tracking the data and results couldn't approve more of that.
The reverse question is how you can measure on field the efficiency.
Yeah.
Sorry, Livio, I didn't quite understand the question.
No, I said the point is how he is assessing the efficiency just on field. Exactly. What kind of setup is using for that? Yeah. It's not so simple.
No, it isn't. In our case, we use a range of monitors in the breathing zone, either commercial grade or reference grade, looking at different particle, broad spectrum particle size. But yes, the standardization in the distribution of those monitors to be able to compare results is the key on that side of the equation.
Okay, if we don't have any other questions from the participant, I think
we do, Giorgio.
Sorry.
I think we have Dr. Alexandro's question about the government fixing the assumptions in the law in order to use these tools.
From who?
Dr. Alexandro. I think the question is, these tools are wonderful, but how to convince government to fix some assumptions in the law in order to use these tools. I can say that for sure we have addressed this issue when people respond to our tool and they say, well, if the government is suggesting 1 person per 4 square meters or 25% of occupancy, your tool is going to be more accurate and more helpful but the regulations that the cognizant health authorities are recommending are different. And that certainly is a problem. One of the things we've done to address that is incorporated to our tool the ability to toggle between the output of the model and seeing what the risk would be if you used a different metric, like 1 person per 4 square meters or 1 person for 2 square meters. And then you could actually compare on a situation by situation basis whether the government recommendations are more protective or less protective. And in many cases, in a poorly ventilated room, we find that the government recommendations on a per square meter basis are vastly underestimating the degree of risk, simply because they don't take into consideration the air exchange. And if you have any type of enhanced respiration rate and or emission rate, then it's going to be even more magnified. So I think this is an important point because there hasn't been much response. I'd like to hear from the other panelists, but I haven't heard much response from governments in terms of trying to do something that's a little more predictive and a little more evidence-based than simply using guidance such as 25% of occupancy or persons per square meter.
Yeah, I would say the best way to fix assumptions is to remove assumptions. There should be more emphasis on actual performance-based measurements as opposed to sort of only design assumptions. We really need a better mix of both. And so introducing performance-based metrics, as has been happening with energy for a lot of building codes around the world, that needs to happen with air quality as well.
But the main question is exactly this. The point is not the emergency now. The point is how to design for the future and to assess the point, to increase the awareness about the air quality, not only for the smell, not only for CO2, but also for viruses like also influenza virus, etc. And then this can be the future for such kind of tool.
And do it in a flexible way. So at the time when there are other risks like significant air pollution outside bushfires and so on, the building can also operate to provide protection, which is the problem we are risking, and do it all in an energy efficient manner.
Yes, this is the way we're trying to work to try to figure out some future standard, let's say, in the way that to balance energy requirement and health requirement, not anymore comfort, but health. That's the point.
Martin.
Yeah, thank you. I know these models are very different from each other, and they really model different things. And in that sense, the comparison between the models may have problems, but it should be done anyway. But something that I noticed that most of the models are missing are personal host factors and the underlying communal epidemic factors. And I just checked, for example, for Helsinki in Finland, for an average person in July and an aged person like myself today, or actually a bit more aged than myself today, with being 80 years old and having a hypertension. The risk between the two situations, the risk difference is over 3,000-fold in similar indoor and social settings. And in that sense, I think that particularly if you're interested in your personal situation or advising people in their personal conditions and choices, this would be very important issues. And this is a difference that cannot be mended by any masking or any social distancing or anything like that at all. The difference by these factors alone is so huge.
But Matti, this is the point that at least on our side, we are trying to build a tool Okay, that means you put some input data, you get some results. Okay, but then this is what you are talking about is epidemiological situation, general local situation, age, sensitivity of people. This is a selection of input on my side. Let me say that. Okay, then you can perform calculation and have an idea of the results.
Yeah, exactly the same thing in my model, yeah.
There's one point that we also have to think of, that many government officials are no aerosol experts, and they are not understanding that aerosols should be a problem. They take their observations, so they talk with medical doctors, they ask how often do you get people that are sick in such situations, and they may just think, oh, well, this is something that is exaggerated. You cannot conclude from a few super spreading events to the whole situation. And this is something I try with this battlefield analogy that I had there. We have few people that are extremely infectious by aerosols. There's about 10% that can infect others by aerosols, and the big mass not. But that's not that we should then say, okay, we just take our strategy for the average emitter, which is like in my battlefield analogy, a paintball kit. So if you are protecting yourself as you would against somebody approaching you with a paintball, then you put on a face shield and all is fine. And this is how you lose the battle. And this is something we need to get into the heads of these people. Maybe an economic model might be better, that you say, if you're a smart investor, you're not going with the average market, but you are going with the top players in the market to maximize your gain. And this is what the virus is doing. It goes with a few that are having very high virus loads, high aerosol emissions, and these are the ones that infect then 20 to 30 to more people at a time. So how to get into the head of these non-experts at the government places?
Okay, I think that it's time. The time is over because we are 2 hours for our webinar. I want to thank the participants, all the panelists, my co-chairman Brad, and of course Lydia. I don't know if Lydia wants to do a final comment. Where is Lydia?
I'm here. I don't think I have any special closing comment. Just thank you, and thank you everybody for making this happen, and thank you Isaac for hosting this webinar.
Okay, thank you for coming. Bye.
Bye bye.
Thanks everyone.
Thank you very much, Isaac, for organizing this. Everybody have a nice day.
Absolutely great.
Thanks.
Thank you.
Bye.